transition. That's perfect. So our speaker today is Kielan Hoch. She is a scientist who's finishing up her PhD at UC San Diego. And one of the cool things, we were just talking about JWST, I know we're excited about things being launched, about it being launched. Kielan will be one of the people who will get to point JWST pretty early on and get to take observations of these really cool, in this case, I think it's young planets, right? And we'll be basically using NIRSpec and MIRI to analyze this multi-planet system, which is really, really cool. So I'll go ahead and let you take it away, Kielan, and you can talk about direct imaging and all these planets and moderate resolution spectroscopy.
Awesome. Thank you so much for the intro. Again, my name is Kielan. My last name is pronounced Hoch, but again, if you look at it phonetically, it looks like you would pronounce it Hoch. So I'm a 6th-year grad student. I'm finishing up my thesis at UC San Diego, and I'm working with Professor Quinn Konopacki. And my thesis is on moderate resolution spectroscopy of directly imaged exoplanets. Over the past decade, the number of exoplanets detected dramatically increased, as shown in this plot from the Decadal Survey. Additionally, each detection method reveals a specific population of exoplanets, depending on their mass and their separation from their host stars. The population that I will be talking about today is the directly imaged exoplanets, shown as the blue dots. Direct imaging has revealed a population of exoplanets that are very massive and are widely separated from their host stars. These planets are very rare compared to the planets discovered indirectly. This slide shows many famously imaged exoplanet systems compared to our own solar system, except for Beta Pix C, that was RV discovered, but I threw it in there anyways. So how are these objects formed? There are two main formation pathways. In the core accretion scenario, a core is formed by an accumulation of purely disk solids. Runaway gas accretion then creates an envelope that will be comprised of entirely disk gas. This will cause an enhanced metallicity in the envelope because the gas, preferentially, will be depleted of oxygen if accreted between the water ice line and the snow and the CO snow line. Core accretion has been successful at explaining the properties of closely separated planets. But traditional core accretion has difficulty forming planets widely separated from their host stars. As the separation increases, there isn't enough planet core mass to continue to accrete an atmosphere, as shown in the plot from Dodson, Robinson et al. 2009. Planets forming through gravitational instability should have roughly the same metal content as the host star. In this scenario, gravitational instability has caused clumping in the protoplanetary disk, which later leads to the formation of gaseous planets. These atmospheres should have close to stellar metallicity because all the material is mixed as they collapse into planets. Gravitational or disk instability can often form planets on wide orbits more efficiently. But again, simulations show that it is difficult to form planets closer than 40 AU. If gravitational instability is so good at forming planets at wider separations, why have we not observed this group of objects? And lastly, gravitational instability simulations have difficulty making the disk fragments stable. So what about other formation mechanisms? Pebble accretion can easily form 3 of the HR8799 planets, but requires special conditions for the outermost planet. HR8799b requires 15 times the normal planetesimal density at a separation of 160 AU. Substantial migration is required due to low pebble accretion rate at that distance, demonstrated by this plot from Johansson and Lambrix et al. 2017. But we can use C/O ratios to try to trace these formation pathways. The core accretion scenario will cause an enhanced C/O ratio that is close to unity in the exoplanet atmospheres. In the gravitational instability scenario, the C/O ratio should be close to the host star because of the separation of solids and gases is irrelevant. This plot from Pisa et al. 2016 shows the C/O ratio estimates in gas and dust as a function of semi-major axis in a viscous disk for CO pure ice and water-dominated ices. Substellar or stellar CO can also indicate that a large amount of icy solids polluted the atmosphere following gas accretion. Now for my thesis. For my thesis, I'm conducting a small survey to obtain moderate resolution spectra of directly imaged companions to constrain their atmospheric properties, C to O ratios, and possible formation mechanisms. For this survey, I used the OSIRIS instrument on the Keck telescope. The performance of all ground-based telescopes are limited by the turbulence of Earth's atmosphere. The Keck Observatory uses an adaptive optic system to remove the effects of atmospheric blurring, as demonstrated with the galactic center on my slides. It's also a photo of OSIRIS on Keck as well. OSIRIS is a near-infrared integral field spectrograph that uses a grid of lenslets in the focal plane to dissect the field of view. The light from each lenslet is dispersed by a grating, producing an array of spectra that are reassembled in data reduction pipeline to an XY lambda data cube, as shown to the left. Also, here is a figure showing the AO system on Keck, the same photo from the previous slide. All right, high contrast direct imaging using OSIRIS is actually first done by Mike McElwain. GQ Loop B, which was discovered in 2005, orbiting a K7 type T Tauri star with a circumstellar disk. Its near-infrared spectrum has been classified as a mid-M to early L, with an effective temperature of 2500 Kelvin and a log G of 4. McElwain concluded that GQ Loop AB is a very low mass ratio, widely separated binary system. Here are some spectral plots from that paper. They're also very special. To the left is J-band with different aged brown dwarf spectra, and to the right is H-band spectra with L0 dwarfs at different ages. Thought I'd throw that out there. So OSIRIS does not have a coronagraph. We have to point to the star and offset from the star to where the planet should be, and sometimes hope for the best. We're usually pretty good with it. The data cube to the right shows what the raw data cube looks like with speckles in all. After reduction, using the OSIRIS data pipeline and following procedures for reduction described in Barman et al. 2011, Kanapeki et al. 2013, and then Wilkham et al., my previous last name, in 2020, bam, we can see our planet. Shown here is a video moving through the wavelength axis of the data cube, showing how the starlight moves with that wavelength dependency and the planet light does not. So sometimes that's how we find the planet visually, by searching through the data cube. All right, for the first planet in my sample, we looked at Kappa Andromeda b. It was discovered in 2012 with the Subaru Seed survey. Here are figures of the discovery by Carson et al. 2013, showing a separation of about 55 AU. We observed Kappa and B with OSIRIS for 3 nights in 2016 and 1 night in 2017 for a total of about 310 minutes or about 5 hours. Kappa and is a member of the 30 million year Columba Association. And using this assumption, Carson et al. 2013 derived a mass of 12 to 13 Jupiter masses for the companion. This means it's a fairly young system. Here is our OSIRIS spectra in all of its glory of Kappa and B. To the right, you'll see a raw data cube slice with lots of starlight from the host star. Then you have after reduction and speckle removal, we are able to see the planet in the center, that middle panel. To the left is our fully reduced, combined, and flux calibrated OSIRIS spectra. Once we have combined and reduced spectra, we use a forward modeling approach in the MC package to estimate parameters such as effective temperature, surface gravity, and metallicity. We do not forward model the telluric star because that was divided out in reduction. The MC code picks a point in the Phoenix model grid space all the way to the top right with a specific effective temperature, surface gravity, and metallicity. Each point in the grid contains a spectra. The code then picks a radial velocity value, a flux offset value that shifts the spectra, and a multiplicative factor that changes the amplitude of the spectra. The code then compares the results to the data, and if the results are closer than the previous point, the program continues to move in that direction in the Phoenix model grid space. If not, it changes direction. Here are the results of the first MC run. We ran the code on both flattened and continuum data. The best fit effective temperature was 1588 Kelvin, a log G of 4.72, and a metallicity of about 0.11. These were not the results reported because we believe there was improper speckle subtraction, especially in the bluer part of the spectrum. Next, we flattened our data by removing the continuum to be rid of those telluric errors from before. The best fit effective temperature was 2048 Kelvin, a log G of 3.77, and a metallicity of about -0.11, which seemed like a great fit. The priors also to the right look pretty decent. To check how our best fit model did compared to photometry and low resolution spectra, we plotted it all together. Plotted here is our model extended over multiple wavebands in gray. Our OSIRIS data is plotted in black. I converted the magnitude measurements into absolute fluxes that were taken over time. Plotted in blue is the Curry et al. 2018 low resolution spectra. Plotted in red is Carson et al. Magnitude measurements. Plotted in light blue is Bonfoy et al.'s 2014 magnitudes. And plotted in purple is Curry et al. 2018 magnitudes. We can also see that the model is a pretty good fit for most of the data and is within most of the error bars. The model does not fit well in the bluer parts of the spectrum, and we believe this is due to clouds. So more modeling and tweaking of cloud parameters could help with that part of the fit, as well as the longer wavelength portions from 3.5 to 5 microns. We really wanted to be sure about our fits because a paper out by Uyama et al. 2020 had a lower temperature of about 1700 Kelvin. Not shown here was a fit for a temperature of about 1700 Kelvin, but it was not as nice as the fit we have even when flattened. We then used two other model grids. One of them was the grid that was used in the Uyama paper. We fit our OSIRIS data with and without continuum, the Curry spectrum, and then the Curry spectrum with just the K band. The two other grids did not have metallicity information to fit for. We then calculated the radius and luminosity to make sure things made physical sense. We then used these values across the models to come up with a range of possible values for Kappa and. I trusted our data in our custom Phoenix models more and adopted the median fits or values from the range of our fits. Our fits also had the lowest chi-squared. We also fit the specs 2 mass object that Curry et al. 2018 said was most similar in spectral shape to Kappa and. Once we had our best fit temperature, surface gravity, metallicity, Travis Barman of University of Arizona created another grid space of Phoenix models that kept those parameters the same and then varied water and CO one at a time. Shown to the right are the chi-squared values of those spectra compared to our flattened data presented in log-log space. The chi-squared results show that the water mole fraction is approximately solar, and the CO mole fraction is approximately solar/supersolar. We back out a C to O ratio by assuming all the C is in CO and all the O is in water. And we end up getting a C to O ratio that is about 0.704. The margin of error includes the C to O ratio of our sun and the host star HR799. We do not have a ratio for the host star Kappa and. The host star is so hot that there are very few lines to model. Wu et al. 2011 modeled the interior of the star to get an estimate for the metallicity, and that value is very close to the value that we estimated for Kappa and B using our MC forward modeling. To demonstrate how sensitive the CO bandhead is to the ratio, I made this plot to the right. Here, I took the models with higher and significantly lower C/O ratios and plotted them against our data to show how the C/O ratio affects the data. Interestingly, I did the same comparison with different temperatures, and the temperatures had a minimal effect on the fit of the CO bandhead, specifically temperatures from 2000 Kelvin to 1700 Kelvin. So no C/O ratio exists for Kappa and due to so few lines in the spectra stated before. So we cannot conclude fully the C/O formation pathway. Our slightly subsolar best fit metallicity for Kappa A and B suggests that the star could be metal poor overall. Many recent works have suggested formation via gravitational instability would preferentially occur around low metallicity stars. The next exoplanet in the sample is a little different. VHS 1256b was discovered in 2015 via direct imaging around an M7 type binary system with a massive separation of 102 AU. We observed this wide orbit target June 10, 2017 using OSIRIS for about 70 minutes total. Here are some figures from this discovery paper, Gaza et al. 2015. What makes VHS 1256b unique is its far separation and the host star/star system being low mass. We did not have to go through the starlight removal in the data cube because of this. We also used a different approach to sky subtraction by nodding up and down on the source and subtracting the object frames from one another. Seen to the right is a reduced and subtracted object frame where the dark spot above is from the other object frame that was subtracted. To the left is the fully reduced flux calibrated spectra of the planet. There are some unusual features in the bluer end of the spectra that we believe is due to improper telluric removal, just as we had with Kappa Andromeda b. VHS is a cooler object that is pretty red, so clouds are going to be more impactful when it comes to modeling the spectra. Instead of fitting for metallicity, we fit for a cloud parameter that defines a pressure value in the atmosphere where the particles decrease exponentially. Fitting for clouds at this temperature and wavelength range is notoriously difficult. Models that treat clouds like a haze tend to give a higher temperature and a smaller radius. When fitting the lower resolution data, such as Gausa and Miles, the fits were similar to what was in the literature. When using models that include the PGS cloud parameter. As soon as we started fitting the OSIRIS moderate resolution spectra, the MCMC code had trouble finding a good fit. It would either be too low or too high. Some models in the grid also ended up having some crazy water features that the fitting code had trouble navigating. We have narrowed down a temperature in a log G range that looks good by eye, and Travis Barman is in the process of creating a smaller grid to better fit the high resolution data. In the meantime, the best fit temperature by eye and by chi-squared is about 1240 Kelvin, a log G of 3.2, and a PGS of 1d6. The metallicity looks to be about solar, though we did not fit for it, and we have no reason to suspect anything other than solar. Shown here is a megaplot of all available data on the object plotted with a close fit model. We do not have the full wavelength range of the model whose parameters fit the OSIRIS data well. So this model is a little off when compared to the available data. Shown in the table is a summary of fits using 3 different custom Phoenix atmosphere grids: ACIS, where the clouds are treated more like a haze; PSO, this is the custom grid that I'm referring to when I'm talking about fitting VHS, where the models are treated with that PGS parameter; and a grid used for the HR 8799 planets and Rufio et al. 2021. We fit all available data and the low resolution spectra and had similar values compared to the moderate resolution spectra. We also fit the host star for temperature, log G, and metallicity, and found out that the host star has solar metallicity. Those fits are not shown in on this page. Taking the best fit parameters that we came up with so far, Travis created a mini grid varying CO, water, and methane. Because of the temperature of this object, methane is an important quantity to take into account. This object was found to have strong vertical mixing in Miles et al. 2018, so we cannot assume all the C is in CO like we did for Kappa and B. I did a chi-squared analysis of this grid and found that the solar abundances for all molecules had the lowest chi-squared value. This will give us another approximately solar C to O ratio. The methane in this grid was not enough to affect the chi-squared that much. So we are recalculating these models and trying to see if we can see a difference when more methane is introduced. We also observed HR8799b, C, and D with OSIRIS, and JB Rufio measured atmospheric properties such as temperature, surface gravity, and the C to O ratios of these planets using a forward modeling approach that involved forward modeling the telluric effects and cross correlation to make the first detection of, or direct detection of HR8799d. Shown here are the posteriors for the 3 planets for the C to O ratio parameter. These ratios all seem to be between 0.58 and 0.54. Although not part of our survey, HR8799e also has a C to O ratio measurement from Mollier et al. 2020 using free retrievals. Shown here is a plot from their paper using the different retrievals against GPy and sphere data, and the C to O ratio is about 0.6 plus or minus 0.7, 0.8. Also not part of our survey, but can you see the trend yet? HIP 65426B's C to O ratio is measured by Simon Petrus in 2021 to be no larger than 0.55 using forward modeling and quote unquote molecular mapping. Shown here are 2 possible fits in black against photometry and spectra of the companion because they had a bimodal function with their best fits. And lastly, Zhang et al. 2021 measured the isotope ratio, the C to O or CO isotope ratio for the very first time, and the C to O ratio of TYC 8998-760-1 or YSIS1. That's what Alex Bond is trying to call it. B, using free retrievals, and shown here is a plot of the retrieval models versus the observed data. And the C to O ratio they found for TYCB or YSIS1B is 0.52. So I am analyzing the C to O ratio formation tracer for these directly imaged planets. Here are C to O ratios that have been recently measured. For this diagnostic to work, we need to have this information for the host star as well. There are projects underway to measure the host star C to O ratios, and we have an estimate for HR8799. For higher contrast systems, measuring the C to O ratio of the host star will be difficult due to the lack of lines in the bright stellar spectra. With this information and the fact that most directly imaged planets have about the same C to O ratio, this formation tracer may not be as reliable as we hoped. Recent works have pondered what could impact this ratio, such as grain size distribution, migration of grains or pebbles, migration of the planets themselves, and whether the accreted material is from the midplane. So what else can tell us about formation of these wide orbit objects? In Mordesini et al. 2012, they stated formation may depend on host star metallicity, which can be reflected in planet metallicity. So in the plot, synthetic planets are the black dots. Lines indicate limiting boundaries of the model. The dotted line is if you force the ice line to be at a specific location and not move around with disk properties. And this apparently helps giant planets form at low metallicities. This green oval represents where Kappa and falls within the errors in the mass range. Most directly imaged planets land on the low metallicity side of things, while the core accretion synthetic planets fall towards the enhanced metallicity side of this plot. All right, Santos et al. 2017 found that there may be two distinct populations of giant planets. Planets that are less than 4 Jupiter masses tend to be around host stars that are metal rich. Host stars with companions that are larger than 4 Jupiter masses were metal poor or solar. This means perhaps low mass planets around metal rich stars could form via core accretion, and higher mass planets could form around low metallicity / solar stars and form via gravitational instability. So we're going to take a step back. We're going to go back to this mega plot I showed before. Even low resolution spectra is hard for ground-based observations past 3 microns. We are missing key pieces from longer wavelengths such as vertical mixing, methane, cloud properties, etc. And as you can see, photometry can only constrain so much. Dun, dun, dun. In comes JWST's NIRSpec. NIRSpec is a near-infrared integral field spectrograph that operates within the range of 1 to 5 microns. It will give us access to moderate resolution spectra, R of about 2700. Without atmospheric turbulence, there is minimal correction needed for incoming wavefronts. So most of the speckles will come from fluctuations in the optical systems and by spacecraft conditions. JWST will open the door for direct imaging spectroscopy beyond 3 microns of wide separation companions, offering a new landscape for measuring planets' fundamental properties, assessing their atmospheres, and testing formation theories. The NIRSpec IFU will be able to perform spectroscopy of sub-arc second companions using similar approaches as proven on ground-based IFUs such as OSIRIS and Symphony. We are working now to adapt and prepare tools and pipelines. GTO, ERS, and GO programs in Cycle 1 will begin employing the NIRSpec IFU to study several high-priority multi-planetary systems and substellar companions, and prove these methods for use on even more ambitious efforts in future cycles. Low-gravity objects such as the young directly imaged exoplanets near-infrared spectra lack methane, which suggests their atmospheres are out of equilibrium. NIRSpec measurements of CO and methane at multiple wavebands can reveal the vertical extent and strength of mixing in the atmospheres of the planets, which can account for non-equilibrium chemistry. With the full infrared wavelength coverage that NIRSpec will give us, we will be able to constrain parameters such as effective temperature, surface gravity, vertical mixing, and metal abundances of exoplanets with more accuracy and precision, allowing us to dive deeper into revealing the formation pathways of these rare objects. Shown here is a plot by Schemer et al. 2014 that shows models of H8799C and D. The pink non-equilibrium chemistry, shows non-equilibrium chemistry, and the blue shows equilibrium chemistry. From 1 to 2.3 microns, shows some minor differences and shows the planets tend to be on level with the pink model. 3 to 4 microns shows how different the models are and shows that both planets tend to be in non-equilibrium. Having moderate resolution coverage of this area will greatly improve our understanding of how these objects work. I am the PI of a Cycle 1 program to image the TYC 8998-760 or WISIS-1 system. We will target 2 recently discovered Jovian exoplanets from Bon et al. 2020 to obtain complete low resolution spectra spanning 1 to 12 microns using NIRSpec and MIRI, and high resolution spectra across 3 to 5 microns using NIRSpec. Common age information environment eliminates uncertainties that can plague comparisons between objects in different systems. TYC 8998 host star is also among the lowest mass stars to host multiple directly imaged exoplanets. Shown here are simulated data cube slices for the planned NIRSpec IFU pointing, Both companions are easily detected even before PSF subtraction. The data cube was generated by combining ETC simulated cubes containing the model planet spectra plus a diffractive model for the host starlight entering the IFU aperture. Shown here are the expected spectra from my JWST Cycle 1 program, emphasizing the amount of spectral information gained from JWST. The strange spectral shape for TYCC is especially interesting alongside how red the object is. I took a combination of Phoenix atmosphere models and BT subtle models and downsampled them to proper resolution for MIRI, and also for NIRSpec medium resolution and for the NIRSpec prism resolution. The black dots are all photometry and the gray spectra for TYCB is symphony spectra. So we'll have probably the most comprehensive spectral library of 2 exoplanets in a multi-planet system ever with this program. With the moderate resolution spectra, we will be able to diagnose non-equilibrium chemistry between CO and methane. We will be able to measure the extent of vertical mixing parameterized by KZZ, which can displace methane from the photosphere with warmer CO-dominated gas. A constrained KZZ measurement will also allow for a more accurate measure of the C to O ratio. And as shown here, this is a plot from my proposal. It is models of TYCB, Phoenix models of TYCB with different levels of KZZ. And as you can see, that spot right between 3 to 3.5 microns is very, very sensitive to this parameter, something that we cannot do from the ground. The shortest wavelengths seen with NIRSpec prism are highly gravity sensitive to constrained surface gravity within 0.1 dex. Alkali metals are present to constrain metallicity that cannot be done with existing photometry. Wide range of atmospheric vertical depths break the degeneracy between the cloud and planet's bulk properties. Shown to the left are models of TYCC at different surface gravities, demonstrating the sensitivity of that region. And shown to the right are different custom models to represent TYCC by Caroline Morley's graduate student, Jessica Luna, to demonstrate the sensitivity to cloud chemistry and composition at these longer wavelengths, specifically between 9 microns and 11 microns. But that being said, more work needs to be done to understand giant planet formation. In summary, we found that Kappa and B to have a C to O ratio of 0.704. We found VHS 1256b to have a C to O ratio of 0.589, or about solar. Kappa and B's host star may be solar, but no C to O ratio is known. VHS 1256b's host star is solar, but no C to O ratio is known. Metallicities that are similar to host star or low metallicities could point towards gravitational instability, but more work needs to be done using that way of thinking before we can actually prove it. And the C to O ratio may not tell us as much as we had previously hoped, with all of the directly imaged planets that have had a C to O ratio measured seem to be about solar or within that same range. Recent work show that metallicity may be a possible fingerprint. And one thing I did not talk about today are recent works done by Yapeng Zhang on the isotope ratios, a possible new formation tracer. She had a Nature paper out this year. But we also asked them to work with us on our Cycle 1 program. So we will be getting isotope ratios of the TYCC planet using our NIRSpec data. And that is it. That is my summary. I will leave it on the acknowledgement slide. Apologies for going a little under time, but I feel like that's better than going over, so there's more time for questions.
Awesome. Thanks, Kielan. That was a great talk. And yeah, totally fine to leave more time with questions too. So I see clapping hands, but if you want to ask a question, feel free to raise your hand and we can go ahead and have Kielan answer them. I have a bunch, but I will wait. Take them. Emily, do you want to unmute and go ahead?
Oh no.
Yay! Hi, Keelan. That was great. No, I loved it. You did awesome. I also have a
Thank
few
you.
questions, but I will try not to bombard you. So for OSIRIS, so you said you have to do, so it doesn't have a chronograph and you have to do the offset to the position of the planet or the companion, right? So does that mean that this isn't really amenable for like detecting new companions and you have to know the position or have an idea of where the position of the companion is when you do the observations?
So that's a really good question. We're actually doing a program on OSIRIS where we're trying to detect exoplanets, but we have to kind of rotate. So we like point it to one side and then we point it to the other side. And then, and then we have to go through that same program of going through the data cubes as they come in and see if we get anything. Yeah, JB Rufio has kind of automated that by using cross correlation. So if we think like, oh, we kind of think that a planet around this will look like this, and he'll usually be able to find it better than anyone. Like he found HR8799D. So, but so it's complicated and hard, but it's fun.
That's awesome. And so I guess in that case, you don't need to know the position of the companion super well, which is unlike gravity, for example, where you need to like place the fiber on the companion and know the astrometry. And what is the resolution of the IFS on OSIRIS?
4,000.
Oh, okay.
At least for K-band. Let me shut the door real quick. Okay. I'm still listening. I'm just going to shut the door. My dog is doing something.
Okay, I'll let other people ask some questions and then maybe I'll ask something else in a minute.
Wait, we can go to Alex. Do you want to go ask your question? Emily, we can come back to you right after that.
Yes. So you say that all of the directly imaged planets seem to have C to O ratios around 0.5, but if you look at cooler brown dwarfs, which are frequently very similar, several of them, like GJ570d and HT3651b, have had retrieved C to O ratios greater than 1. So have you seen any models that explain that?
Other than core accretion and pebble accretion, those are the only real models that I'm aware of that can give you those higher C to O ratios. It's very interesting that even low mass brown dwarfs are having ratios that high. So again, it's a mystery and one of the reasons why we gotta figure this out and look at how these objects are forming.
Emily, do you want to go ahead with your next question, and other folks, do you want to raise your hand?
Yeah, sure. So I see on the spectrum of Kappa and B that you mentioned, and you can see that the shorter wavelengths, it doesn't really agree with the like the spectrum that you derived doesn't agree with the shorter wavelengths, if I remember correctly. And I was just wondering, exactly. I'm just wondering what observations we can take to disentangle this, but so I guess NIRSpec could be a good option. Also, I was thinking that maybe we could put in a MOSFire proposal.
That would be really cool.
Yeah, because I was just looking at the wavelength range, and it seems that it'd probably be doable.
Yeah. I mean, a lot of the limiting factors too are, at least with forward modeling, something that we don't have, like the free retrieval people have, is that we can only fit for so many parameters. So once you kind of have a good idea on what the temperature and surface gravity of this object might be, that opens up the doors to creating these custom models with different cloud layers, different types of clouds, different stuff in clouds, because like a lot of they just kind of impact that J band area, and they impact the longer wavelength range as well. So as soon as we kind of are more certain with that, then we can kind of explore more options with forward modeling. But it would be interesting to see a free retrieval on on Kappa and.
Yep. Okay. Thanks.
Avi, do you want to go ahead?
Yeah. Hi. Great talk, Kielan. I was really intrigued, of course, we all are, somewhat by the CentOS 2017 suggestion that mass is actually a defining sort of parameter that may reveal planets formed by one, especially at the high end, differentiating. Are there other, from those models, if you, I guess I'm just now I'm asking you to talk more generally about this idea, if you've read into it. If you form a high mass planet through gravitational collapse versus a somewhat lower mass planet building up through core accretion, it seems beyond just chemical markers, there might be other sort of aspects of the planets, whether it's obviously the temperature, cold, hot, whatever, even the internal structure, something about the, layering or maybe sequestration of refractories that would be different. Are there other, maybe, obviously the theory maybe hasn't been developed enough, but are there other lines that people are taking along this?
At the moment, not that I am aware of. I know metallicity and like this new mass differentiation is pretty popular right now. But again, it's one of these things where we just need to be doing these studies and getting all of these atmospheric properties of these objects. And it is just notoriously hard to do this with planets that are less than 4 Jupiter masses. So, I think that we need to get the data there so we can start testing some of these more involved theories, because, perhaps the C to O ratio is too simple for the formation of all of these objects. But again, we need a larger sample size. And I believe that with everything going on with JWST and how exoplanets are now kind of a really big hot topic right now, I'm hoping that more and more data will come through so we can start kind of seeing trends, like, most of them are having C to O ratios very similar to one another.
Awesome. Thanks. Kielan, so I'm going to sneak in for a question too. So you mentioned the upcoming observations. You'll be looking maybe at isotopes too. Can you talk a little bit more about that and what you hope to see?
So we asked Yaping Zhang and Alex Bond to be on our program, and so the thing I can speak about, I can't speak too much about the isotope ratios. I'm not an expert, but it is another way to kind of trace where in the disk that these objects formed, and it may be less polluted, less chemical reactions and stuff happening to that ratio compared to how polluted maybe the C to O ratio can get. So that's kind of the idea that I took away from the new isotope ratios, that will hopefully maybe give us another parameter or something to look at, maybe open up new ideas to other things that we can start looking at in the atmospheres of these objects.
So I think William had something right along that line. They were asking, is a 12 to 13 C to O ratio something that you can obtain from the OSIRIS data?
We might be able to obtain it from OSIRIS data, actually, because they were able to obtain it with Symphony data, I believe. So they might be able to. They could do it with probably Kappa and B, so like the brighter objects. But the more fainter, like 2ICC, they couldn't do from the ground. So we're going to give them NIRSpec data to do that for them. But I think some of the brighter objects, they could probably start knocking out some isotope ratios.
And that's super exciting. I can imagine too, if you have a multi-system, you can actually trace things like fractionation and all this other stuff that you extricate where in the disk you were, and then maybe some of kind of the evolution as well, which is really, really cool. Usually I only think of doing in our syllabus, so that's awesome. Let's see, I think we have another hand. Emily?
I promise this will be my last question, Keelan. And I feel like I should know the answer to this because I'm on your program. But for the NIRSpec expected prism spectrum for TYC 8998, it was different. The expected spectrum was different to the VLT photometry from Bonatel. And I was just wondering if you could comment on why that might be. Yeah, like in the shorter wavelengths, yeah.
Yeah, so this was actually the best fit BT settle model from the bone paper, because I mean, a lot of the atmospheric models that we have for objects at these temperatures do not look like this. This looks like an upside down bell to me, or like literally a Gaussian distribution. So like the spectral features of this object are just very, very strange. And there's only, you know, 1 or 2 models I could find that kind of like fit that shape in general. So they do struggle to fit the VLT photometry for sure. They're kind of inside of the uncertainty a little bit, but yeah. I mean, that's one of the reasons why we want to go look at it and get higher resolution spectra, because this object is probably one of the reddest that we've seen too. So it could probably inform us a lot about what's going on in the atmospheres of some of these like cooler, redder objects, and perhaps like help the models fit them a little bit better.
Yeah, I'm really excited to get our hands on that NIRSpec data. It's going to be exciting soon, hopefully soon. And again, that was a really great talk. I won't ask you any more questions, I promise.
No, thank you.
Let's see, any last questions? Go ahead and raise your hand. I'll ask one more. You mentioned Kappa Andromeda and awesome, bright, you know, star system. Have you thought, because you had the models on there and kind of that blue discrepancy, have you thought about what you would see in the visible and how you could maybe use metallicity constraints from like potassium or sodium to extricate kind of formation?
That's really interesting. I haven't thought about that. We tried to get J-band data on Kappa and, but we couldn't really find the planet in the data cube. So it was way more bright and easier to do in the K-band. But again, that kind of limits our, you know, metallicity measurements in general. So it would be very interesting to get an optical or, you know, push to shorter wavelengths for Kappa and. I know that my advisor Quinn has a grad student that is working on host star metallicities and trying to, you know, obtain data of all the host stars and try and give us some sort of like, you know, baseline for some of them. And I know that one of the host stars that he's working on is Kappa and. So
awesome. Looking
forward to that.
I think I see, William, do you want to go ahead and unmute and ask that question? I can also read it. I can go ahead and read off the question then. So it says, have you tried fitting a model plus black body, like a circumplanetary disk to the C planet to fit the red VLT photometry?
I have not tried that yet. So that's definitely a really good idea. I haven't really paid or haven't really done a lot of work on circumstellar disks yet, or, you know, fitting what did you say, black body? Did you say black body?
Yeah, it's
okay, yeah.
Black body.
Yeah. So it is definitely something that would be cool to do, but I've not done it yet.
All right, so we'll do a final call for questions, but then you can also email Kielan.
Yep.
And I don't see hands. So let's all give Kielan another thank you and a hand for a really cool talk, a really interesting talk too, and very prescient with, you know, hopefully JWST launching soon and getting to take these cool observations.
Thank you so much. Thank you all for joining.
Thank you.
I need to find my mouse. I found it.